Hi everyone. Today we're going to continue our work on Taylor series. So if we go back to our last notes, right, we defined a Taylor series for some function f of x, an infinitely differentiable function on an open interval containing some value a. The Taylor series generated by f of x at x equals a is f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared plus f triple prime of a over 3 factorial times x minus a cubed, etc., etc., etc. And we have the sigma notation right here. Okay. Now, along with that, right, very often when we talk about Taylor series, what we're really going to be looking at are Maclaurin series. Is that a word? I don't know. Which is just a Taylor series centered at x equals 0. So in the last notes, we wrote a couple of Taylor series. We did it for e to the x power, right? And then towards the end, we did it for sine of x as well. Okay, so we're going to continue on some of that on that same route and write some Taylor series for some common functions. So to today's notes, right, reviewing the Taylor series for sine of x, right? We can go ahead and copy and paste that if we want, or write it down again from the last notes. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial minus x to the 11th over 11 factorial plus dot, 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 dot. And so we talked about this in the last video, but one thing you are going to be expected to be able to do when finding the Taylor series for any function is take that series and represent it in sigma notation. So this is similar to what we've done in the past. We're still just trying to look for patterns that we see with the terms. So one thing I noticed right away, the flip-flopping part of it, right? So -1 to the something. I want to make sure I start off with a positive coefficient here. I'm choosing to make n equal to 0 as my starting term, which is typical, when you're being asked to do this on, let's say, a quiz or test, right, and you choose n equals 1, right, you're going to get something that represents these same terms, right? As long as it's equivalent, right, it will be accepted. Just remember on multiple choice, though, very often n equals 0 is actually the starting value. So for n equals 0, right, I need -1 to the n. I'm having odd exponents, right? And so it's going up by 2, so that's where the 2n comes from. But I'm starting with an exponent of 1. That's why I need plus 1. And whatever that exponent is the number in the factorial in my denominator. So 2n plus 1 factorial. And then interval of convergence, -infinity to infinity. Now, we're going to use this, right? And we are going to find the Taylor series for cosine. And so we have to now think about, okay, what can I do with the function sine of x to turn it into cosine of x? So first thing I'm going to do here is I'm going to delete that and just show you that all I've done here is copy my first few terms from the Taylor series for sine of x, right? And now, okay, so what can I do to take sine into cosine? Remember, this is calculus, and so one thing we can do is take the derivative, right? So we can take the derivative of every single one of these terms, and that will give us the Taylor series for cosine of x. So let's go ahead and do that. So cosine of x equals, let's take the derivative. Derivative of x is 1. Derivative of -x cubed over 3 factorial. The 3 comes down. Now remember, it goes to the numerator, so the 3 cancels with the 3 factorial, which is how we just end up with 2 factorial. And that's going to happen on all of these terms. So the exponents all go down by 1, and the factorials in the denominator also go down by 1. Sigma notation, right? Again, starting at n equals 0. Still starting off with a positive term. For cosine of x, I have all of the even exponents, so x to the 2n, and then the denominator 2n factorial. So these are ones that we can generate and come up with. Now we're going to take a look at a few that you have to memorize. So again, very often when we're talking about Taylor series, what we're really looking at though is a Maclaurin series, right? And so that's for cosine of x and sine of x here as well. So those are two of them. here are 5 more functions whose Maclaurin series, Taylor series you are going to be expected to know. So the first one here is 1 over 1 minus x. And this is actually one that we did a few note sheets ago, right? So the terms for this one are 1 plus x squared plus x cubed, right? This was from our power series day 1 notes, right? This is actually this summation here, right, comes from the sum of an infinite geometric series, a sub 1 over 1 minus r, right? R here is x. And so we have it in sigma notation, right? Again, starting at 0, this is x to the n. And since r is equal to x, this is going to converge when the absolute value of x is less than 1 or x is between 1 and negative 1. Now, this is something we'll talk about later on as well. How can I do it for 1 over 1 plus x? Well, 1 over 1 plus x is really just 1 minus negative x. So I'm going to replace the x in our previous series with negative x. So every x here gets replaced with a negative x. And so, right, for all of the even exponent terms, right, those are going to stay the same sign, and all of my odd exponent terms, those are all going to become the opposite, right? And so going from one term to the next, I'm multiplying by just negative x, right? And so in sigma notation, 0 to infinity, negative x to the n. And so my r here is negative x, right? And so since I'm taking the absolute value of that to be less than 1, it doesn't matter if it's positive x or negative x, right? So it's the same interval of convergence as the previous one. E to the x, we did in the previous note sheet. The first term is 1. One thing to remember, just kind of a funny thing you learned when you did, combinations, permutations, all that fun stuff, where you first learned about factorials, is that 0 factorial is actually equal to 1, along with 1 factorial. So 1 is over 0 factorial, x is over 1 factorial, x squared is over 2 factorial, etc., etc. So we have e to the x in sigma notation, right? And that one converges for all x values, negative infinity to infinity. So that's nice. Natural log of 1 plus x. This one's a little interesting. So this is x minus x squared over 2. Notice there's no factorials here. Plus x cubed over 3 minus x to the 4th over 4th. And so in general, right, my term is negative 1 to the n minus 1 power. Now you could write n plus 1 power, and it's the same thing, times x to the n over n, right? And we can go ahead and write it in sigma notation, which you already had in front of you, right? But I wanted to do a grand reveal because for this formula, right, this one starts at n equals 1. And this is our only one that we have to memorize that starts off at n equals 1. And then this one is only going to converge when x is between negative 1 and 1. But another one thing that makes it a little interesting is that the 1 is inclusive for this one, okay? Our last one is for a function we did a couple of note sheets ago as well, arctangent of x or tangent inverse, x minus x cubed over 3, again, no factorials here, plus x to the 5th over 5 minus x to the 7th over 7 factorial. So this is negative 1 to the nth power times x to the 2n plus 1, right, because I want every odd exponent, and that exponent is also my denominator. Okay, so here we have it in sigma notation, again, starting at 0, and the interval of convergence for that one, absolute value of x is less than or equal to 1. So this one is the only one where it equals 1 and negative 1 on that. All right, and so just the last thing with these, right, these are all the ones you have to memorize. So, these 5 right here, cosine of x, sine of x, right? These are the ones that you are going to be expected to know and to be able to use. And just a little fun fact, right? Maybe something heading your way in the future about these. All right, so let's see how we can use these. Group problem 1, find the Maclaurin series for f of x equals sine of 3x and give the interval of convergence. So the question here specifically says Maclaurin series, right? In my notes, often I'll write Taylor series, right? But we have to remember a Maclaurin series is a Taylor series, so it's all good. So for sine of x, right, one way to think about it is I am going to think of it as sine of box, okay? Sine of box, right? If I go back up to what we have at the top here, right? When the box is x, right, the series is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc., etc. But when it's box, the series is box minus box cubed over 3 factorial plus box to the 5th over 5 factorial minus box to the 7th over 7 factorial. And so when you are trying to find a Maclaurin series, right, so this is very critical. This only works for this type of question, right? When it's centered at 0, you can let that box be anything, right? And so in this case, I'm going to let the box be 3x, right? So the Maclaurin series for sine of 3x is going to be quantity 3x minus quantity 3x cubed over 3 factorial plus 3x to the 5th over 5 factorial minus 3x to the 7th over 7 factorial. And the interval of convergence is not affected by replacing the x with a 3x, right? You can divide everything by 3, and x is still infinite on both sides. So again, this is a strategy you can use when you have a Maclaurin series. And of course, you could simplify this, right? Cancel stuff out, things like that. We're not going to worry about that today. Okay, let's keep going. B, find the Maclaurin series for f of x equals x over 1 minus x to the 4th and give the interval of convergence. So this one's tricky. The goal here is to do something similar to what we did on the last one, right? But the last one is very obvious. If it's sine of 3x, I should use the Taylor series for the sine function. But what should I do for x over 1 minus x to the 4th? And so this one you have to be careful with, right? One thing I'm going to tell you to do here is you can think of that numerator part of it as kind of separate. So let's say instead of it being x over 1 minus x to the 4th, what if it was 1 over 1 minus x to the 4th? Which of these Maclaurin series would you use, right? I would use the first one, 1 over 1 minus x. I can let that just be 1 over 1 minus box, and I'm going to follow the same strategy I did as above. So I'm going to do the Taylor series for 1 over 1 minus x. So again, think of it as 1 over 1 minus box. And so that series would be 1 plus box squared plus box cubed, and it would converge when the absolute value of box is less than 1. So same strategy as last time. Right? Again, I can do this because the question is asking for a Maclaurin series, so it's centered at 0. I can go ahead and substitute in x to the 4th power for the box. And so what do I get when I do that? 1 over 1 minus x to the 4th. I get 1 plus box x to the 4th plus box squared x to the 4th squared plus x to the 4th cubed plus x to the 4th to the 4th, etc. And this will converge when the absolute value of x to the 4th is less than 1. So I have a series for this function. How can I get it to be the one the question's asking for? And so this is where we can bring the numerator back in, right? What can I do to this 1 to turn it into an x? I could take my entire series and just multiply it by x. And so I can take that, right, multiply it into the numerator, multiply it then into every term I have here. And so when I do that, right, I will get x plus x to the 5th plus x to the 9th. Remember, exponent to an exponent, you multiply, and then we're multiplying by another x, so we add 1 to get these exponents, 1, 5, 9, 13, 17, 21, etc., etc. And now for the interval of convergence, you can take the 4th root of both sides, right? And you still get absolute value of x is less than 1. Okay, C, find the Maclaurin series for f of x, big F of x, equals the integral from 0 to x of t over 1 minus t to the 4th dt, and give the interval of convergence. So we have a different variable here, but this is actually the same question as b from above, except now we're going to do a definite integral of our answer from part B. So just going to start off by rewriting the question. Okay, and now I'm going to go ahead and do the integral of my answer from above, so taking this answer right here, but now all of my terms are t, right, because x is part of the bounds of my integral. So this is t plus t to the 5th plus t to the 9th plus t to the 13th plus dot, 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 dot. And the whole thing here is being multiplied by that dt. So I really should put parentheses around all of that to get the dt there at the end. And then interval of convergence, right? So, here it was x. In this question, it's t. So absolute value of t is less than 1. And so all I'm going to do here is just do my antiderivative, right? Take all the terms here, do their antiderivative. And so just follow normal rules, right? So for t squared over 2, t to the 5th, t to the 6th over 6, t to the 9th, t to the 10th over 10th, t to the 13th, t to the 14th over 14, plus dot, 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 dot. And so that's for all of my infinitely many terms. And now, fundamental theorem of calculus, let's plug in x and let's plug in 0. One nice thing we should realize right away, when we plug in 0, all of these terms would go away, so I don't have to worry about that. And so I get an answer of x squared over 2 plus x to the 6th over 6 plus x to the 10th over 10th plus x to the 14th over 14th plus dot, dot, dot. Right? We can replace the t back with an x because we're plugging in x for t. Absolute value of x then has to be less than 1. Last thing, and this is just good to practice, maybe this is a point where you want to pause the video and try to take your answer here and write it in sigma notation yourself. So I'm going to go ahead and reveal the answer right now. So this might be a good time to pause and practice this yourself. Okay, so very commonly, I'm going to start at 0, right? N equals 0 to infinity, 2, 6, 10, 14, right? So my first exponent is 2, so plus 2. And then what am I going up by for every term? I'm going up by 4. And then that becomes the same number in my denominator as well, so 4n plus 2. Okay, let's keep going. Example 1. Find the Maclaurin series for e to the x plus e to the negative x over 2. So this one, right, it's kind of telling us which Taylor series we should go back and look at, right? E to the x plus e to the negative x, right? Let's go ahead and use the one for e to the x. All right, and so the same thing applies, right? If it's asking us for a Maclaurin series, it's centered at 0, right? So we can go ahead and use that box strategy. So what's the Taylor series for e to the x? I'm going to think of it as e to the box, and so I would get 1. The first term is 1, can't replace that with anything. Plus box squared over 2 factorial plus box cubed over 3 factorial plus dot, dot, dot. And I'm just going to do this twice. I'm going to do this and let box be x, and that's going to give us the Taylor series from the first page. And then I'll do it again and let box be negative x, and then I can take my two series and add them together. So first, let's do this for box equaling x. And so this is, again, just the one from the first page of notes. Pardon me, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, dot, dot. And you can see I have some stuff slashed out here because when I go ahead and do this for letting box equal negative x, e to the negative x is 1 plus a negative x, so x plus negative x, right? I want to add these two series together so I can add the terms together. Those are going to cancel. Negative x squared becomes positive x squared, so these terms will not cancel. But negative x cubed becomes, well, just negative times x cubed, so these terms will cancel. So all of my odd exponent terms will cancel. All of my even exponent terms will get doubled. And so when I add these together, I am going to get, for e to the x plus e to the negative x, go ahead and add all of these terms up. I get 2, plus I get 2 x squared over 2 factorials. I get 2 x to the 4th over 4 factorials, plus I get 2, the next term would be x to the 6th over 6 factorials, right? And now again, I could, simplify this stuff. You are all capable of that algebra, right? But remember that I'm trying to divide all of this by 2. So that's my next step. Take this answer and divide everything by 2. And very conveniently then, all of these 2's will get canceled out. And so I get a final answer of e to the x plus e to the negative x over 2 equals 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial plus x to the 6th over 6 factorial. And again, this might be a good time for you to pause. Try to write this series in sigma notation. I'm going to go ahead and reveal the answer now. Okay, so again, I'm choosing to start at 0, so 0 to infinity. My first term has no x's in it, and then I go x squared, 4th, 6, so I'm, just powers of 2 every time, or multiples of 2 every time. So 2 to the n is my power, and then that's the same number in the factorial in the denominator. All right, let's keep going. This one's a little tricky. This is a good tricky question here. Determine the function that is represented by the following series. So very often, right, what you're going to get for a question like this, the question might say something like, represent this series using common functions, something like that, okay? And so for something like this, what you're trying to do is you're trying to look at this and you're trying to go backwards. I'm trying to look at that question and go, which of these 5, 6, 7 Taylor series does it remind me of? And so you may have to do a little manipulation. Think of the e to the x plus e to the negative x question, right? We may have to do a little manipulation, right, in order to get our answer. So the first thing I notice right away is I have a 2x here. This one also has a 2. None of my other terms have a 2 though, right? And that's a little weird. And so what I'm going to do first is I'm going to divide every term I have here by 2x. All right. So when I do that, what do I get? So when I say divide, really I'm just factoring, right? I'm going to factor out a 2x. And so again, how did I know to do that, right? These two terms have a 2. Looking at my exponents, 1, 4, 7, 10, 13. Right? That's a weird pattern. Going up by 3 is fine, but starting with 1, right? If it was like 0, 3, 6, 9, right? I would be more okay with that. That seems like a more reasonable pattern to me. So that's why I chose to divide out a 2x. And so divide everything by 2x, so I get 1 plus x cubed, plus for this term, x to the 7th, I would get x to the 6th divided by 2. I'm going to choose to write this as 2 factorial. X to the 10th, divide by x, I get x to the 9th, right? If I divide by 2, that puts a 2 in the bottom. 3 times 2 is technically a times 1 as well, right? So that's 3 factorial. This is where it gets a little tricky, right? 12, right, is the same thing as, 4 times 3, right? But if I put a 2 there, right, now it's 4 times 3 times 2, which is just 4 factorial, and this becomes x to the 12th, right? And so if I look at these terms, right, no denominator here, or, denominator of 1, 2 factorial, 3 factorial, 4 factorial. And if I go back to my list on the first page, that looks a lot like e to the x, okay? And so I can say that this right here in the parentheses, that is e to the box, where box in this case is x to the 3rd power. Right? And that's how I get that pattern of 0, 3, 6, 9, 12 for the powers of x's. And so I can rewrite all of this, right, as e to the x cubed power, right? And then with the 2x that I factored out, this whole series becomes 2x times e to the x cubed. All right. So yeah, that's a little tricky one to end on. You'll definitely see more of that in the future. We'll practice some more of that. All right, that's all we have for now. So I will see you all next time.